So in order to kind of generalize this process for the number of rectangles so that we can use any number we want, we're going to come up with a formula for the right rectangular approximation method. Now we could do this same thing for the left rectangles, the midpoints, or the trapezoids. All four of those methods are going to give very accurate answers when we have a lot of rectangles. The reason I'm choosing the right rectangles, and most sane people would choose the right rectangles, is because the formula ends up being a lot cleaner than the other methods. Okay, so with only a few rectangles or a few subintervals, the right rectangles are usually not as accurate as trapezoids. But if we increase the number of rectangles to a really, really large number, that accuracy increases significantly. So we're going to use the right rectangles. So I want to just kind of look at a picture here and kind of get an idea of what's going on, and we're going to generalize this. So we're not going to just set a number of rectangles, but we're going to say if there are n rectangles. So meaning we're going to use n subintervals. Another thing that we're going to do to simplify this process is we're going to say that those subintervals are of equal size or equal width. You don't have to do this. We talked a little bit about Riemann sums yesterday. Riemann sums work and can be very accurate with unequal sized intervals. But with equal sized intervals, it makes the formula nice and clean. So that's why we're going to use equal sized intervals. So the first thing we're going to do, remember, we're trying to approximate the value of an integral here. So we're trying to approximate the integral from a to b of some function f of x with respect to x. And again, this dx here, this differential, that means that we're moving along the x-axis and finding the area between this function and the x-axis. Okay, so we're trying to approximate this using right rectangles, so the right rectangular approximation method, with n rectangles. And that variable n is the key here. This is what's going to make it all work. All right. So since we're going from a to b along the x-axis, first thing I'm going to do is just mark off. It really doesn't matter here. Just mark off an interval here from a to b. And we're going to break this up into rectangles. So let's just get an idea of what that's going to look like. I drew the picture this way because we don't know how many rectangles there are. We're going to make it variable. So I put these ellipses in here to show that there could be really any number here. Obviously, the more there are, the smaller these intervals would be. So I just drew in 4 rectangles here, and that's going to help us with kind of coming up with this formula. So we're going to start at A, we're going to go to B, and the first thing we'll want to do is figure out how wide each one of these intervals is. So how do we figure out how wide each sub-interval is going to be? Yeah, so to figure out what delta x is, and delta x again is going to be the width of any one of these intervals. To figure out how wide each of those subintervals is, we take the width of the entire interval, b minus a, and divide by n. All right, so that's going to become part of our formula here. We'll use that in our formula. We're also going to label each of the x values here along the x-axis. So we have an x value here, we have one here, we've got one here, we've got one here, and we're going to have n plus 1 of these actually. We don't have n of them because, well, each subinterval has a left endpoint and a right endpoint, so it ends up being n plus 1 of them. So if you remember the notation we used yesterday, we called that x naught or x sub 0, x1, x2, x3, all the way up to x sub n. And so the one to the left of x sub n would be what? X sub n minus 1. And we could, that's an x, we could work our way back, and eventually these are going to meet up. We don't know how many rectangles there are. We're trying to make this as generic as we can right now. All right, so we know those x values. We also know the width of this interval right here. We know that's delta x. We also know this is delta x. We know this is delta x, and so on. So one other thing that we're going to want to know is what those x values are. So what is x naught? That's just A, right? How would I figure out then what x sub 1 is? A plus delta x. And so x sub 2 would be, yeah, A plus delta x, which would be A plus 2 delta x. All right, and if you see a pattern here, patterns are good when we're trying to come up with general formulas. If you see a pattern, that'll help here. So what's x sub, let's go I. What's x sub I going to equal? I'm not going to use n because I don't want you to think that I mean this x value right here. So what's x sub I going to be? A plus I delta x. Okay, cool. So we know each one of these x values. And we can get each one of these x values by using this formula right here. All right, so we know what delta x is from this formula. Then we can plug it in here, and we can figure out the x value for any subinterval by using that formula, the left endpoint plus I times delta x. So if we're looking for the fifth one, that would be 5 times delta x. And so now we're getting to the point where we have enough information we can start finding some areas. So this right rectangular approximation method, we're going to use, obviously, the right rectangles. So how do I figure out the area of, let's just say the first one here. I want to find the area of that one. What's it going to be? Delta x times f of x sub 1. Okay, so we're not using the x sub 0, are we? Okay, we're starting with the x sub 1 because x sub 1 is the right endpoint. What's the area of the second one going to be? Now, a lot of what we're doing here is going to seem very similar to what we did before, except we had kind of a set number of rectangles before. And this pattern is going to continue, right? It's always going to be delta x times f of x sub whatever the interval is. So if I wanted to generalize this, a general term in this sequence or series would be delta x times f of x sub I for the ith term. And then we would continue on until we get to the last term, which would be delta x times what? X sub n. So the very last one is going to be x sub n. Let's try to clean that up a little bit. The very easiest thing to do to clean that up would be to do what? Factor out that delta x. We have a delta x in each term, so we can factor out that delta x. Now, when we factor out the delta x, what's going to be left is f of x sub 1 plus f of x sub 2 plus f of x sub 3 all the way up to f of x sub n, right? So we can rewrite that sum using what? Sigma, summation notation. So we're taking f of x sub I, and I always like to write the general term in a series because then we can just use that general term in our sum, in our sigma. And I is going to start where? I starts at 1 and it's going to go to n. So this whole thing right here simplifies to that. And we don't even need the ellipses, which is kind of cool, right? So we don't even have to guess how big this is going to be. We just throw the n as our upper variable and we're good. Now, we also have a formula for x sub I, don't we? We know what x sub I is. What is it? A plus I delta x, right? So this is going to be the same thing as delta x times the sum from I equals 1 to n of f of a plus I delta x. And this formula right here is going to allow us to use the right rectangular approximation method to approximate with any number of rectangles. Now, there's a problem with this, and we'll deal with this problem in a little bit. But the problem is, even though this looks really simple and nice and clean with the sigma notation, you guys might be thinking that doesn't look simple at all. It's a lot simpler than it started, though. Even though that's the case, with the sigma, we still have to do n computations. So if n is 100, we still have to add 100 different terms together, right? So it didn't really save us that much work yet, but we've got it in a form that if we figure out ways to simplify that summation, then, then that's going to help us out. All right, so this formula right here is going to be something that's going to be extremely valuable for us. You hopefully have it written down already. But this is the formula to find the right rectangular approximation of any definite integral using sigma notation for any number of rectangles. All right, so our next task then is to figure out how we can simplify this sigma so that we don't have to do n computations. We don't have to add 100 rectangles together when n is 100. All right, and that's our goal.